Okay, we're in A2Further Maths here. We are on chapter 7 and we're now looking at reduction formula. So it says here reduction formula could be used to find indefinite integrals, which was our previous example if you look at the previous video there as above, but more often they are used to evaluate definite integrals. So that's what we have here. Find the reduction formula for I to the n, the integral between pi over 2 and 0 of sine to the power of n x dx, where n has to be greater than or equal to 2. A few wee tricks for this one, a few wee tricks of the trade, but we will get there with it. So if we take the original question and we put between pi over 2 and 0 of sine to the power of n x dx, the wee trick for it, and again you just learn this with a wee bit of practice, is we're going to rewrite this quite strangely, it might seem. Sine n to minus 1 of x, so we've taken 1 off the power here, and then times by sine x dx. We're going to let then, obviously we're going to use integration. How's the light there? Is that a bit odd? That makes it worse for me. Hopefully you can see that okay. We're going to let u equal then sine to n minus 1 of x, and we're going to let dv by dx equal sine x. That means du by dx, I hope we're okay with this, is going to be n minus 1 upon sine to the n minus 2 x cos x, and then v is comparably straightforward. We end up then with minus cos x. So our integral then in this case is uv, this times this, which is minus sine n to minus 1 of x cos x between pi over 2 and 0. Take away the integral of v du by dx, so it's minus n to minus 1 sine n minus 2 cos x, and I get the minus from here to there, and that's times cos x again, so that gives me then the cos x squared. So remember I'm doing the v times the du by dx, and we end up with that then. That means our original question, and let's write it out then just separately so we don't really start to confuse ourselves. Sine to the n x dx is equal to uv. Now incidentally, there's a wee important bit here. This always goes to 0. Because we have pi over 2 and 0. If you find the sine of pi over 2, that's 1, but the cos of pi over 2 is 0. And then the sine of 0 is 0, and the cos of 0 is 1. So you're always multiplying by 0 no matter what you're putting in, so that bit disappears. Plus, the minus and the minus there change to a plus. And also I'm going to take out the n minus 1. And we then have the integral between pi over 2, and what we left with here, sine n minus 2 x cos squared x dx. My next move here is to change this cos squared x into a 1 minus sine squared x. So this equals that 0, we'll just obviously leave, so we have n minus 1 upon the integral pi over 2 and 0 sine n minus 2 of x 1 minus sine squared x dx. And tidying again, we're away for space, I think we should be okay. And minus 1, and I'm going to separate these two out because you're going to multiply through here by 1 and multiply through here then by sine squared x. I'm going to actually do two different integral signs. I hope you can follow this okay. Pi over 2 and 0 times by the 1, we end up with sine n minus 2 of x, and then minus the integral between pi over 2 and 0. So here I'm timesing this by this, and of course that gets rid of the 2 there, so you just end up with the original question of sine nx dx. Should be a dx probably there, but that's okay. Put ourselves away with it. Of course, I to the n, we've written at the very start, is the integral between pi over 2 and 0 sine to the power of n x dx. That means this here is going to be I to the n minus 2. And that's the integral between pi over 2 and 0 of sine n minus 2 x dx. So that means our original question, if you can work out where we are this here, and this line here, that's an in is equal to n minus 1. I'm going to keep this wee bit actually separate. So confuse this as a line, those are just defining those things. N minus 1 multiply with our brackets again, I n minus 2, take away n minus 1 in. We're trying to work out our reduction formula, so we need the I on its own, so we're going to take this over then to this side here. So we have then I n plus n minus 1 I n minus 1 I to the n minus 2. You've in plus n minus in, so those in's are going to cancel. You just end up with then n minus 1 I to the n minus 2, and that means our reduction formula is going to be n minus 1 all over n minus 2. In the next video we're going to use this then to solve specific ones.